Okay, so now I'm ready to do the trivial problems that I promised you in the previous video. And so before I do that, though, I want to give you a method of attack for these kinds of problems, one that I've found over my 35 years or so of teaching is very helpful for students. It helps them to be able to focus and not get overwhelmed by a problem, no matter how complicated. After I go over these, we'll do a few simple problems in which I will try to illustrate how they're used. So the first thing you do is choose a body. Now, in the examples that I do on this video, there's never going to be any question about which body we should choose, because there's only going to be one actual body in the problem. But in general, this is the most important part, to realize that often you're not going to be able to solve a problem all in one fell swoop. You're going to have to solve first part of the problem and not have solved the whole thing yet, and then another part, and then maybe another part yet. Second, once you've chosen your body, then you draw a diagram of that body and find all the forces on that body. Now, your book probably uses the expression a free body diagram, and that's fine if you want to call it that. I think that's very descriptive. Basically, it means a picture of the object and all the forces that are acting on it. Now, that doesn't mean that you know all the forces on that body. In fact, the forces will often be the unknowns in a particular problem. So you have to recognize that if there's some force that you don't know, you have to acknowledge its presence. And when you draw that force on your diagram, you can incorporate what you know about it. If, for example, you have some way of knowing the direction of that force, then you can draw the force in that direction in your diagram. But often you won't, and you will just have to draw some random force and solve for it. That's what the problem is all about. Number three, once you've chosen that, choose a coordinate system. Now, there is no right or wrong coordinate system. There are, however, good and bad coordinate systems. Any coordinate system will work. Often you can make your work easier by choosing a coordinate system cleverly. For example, if there's an object that has a half a dozen forces on them, and 4 of them are perpendicular to each other, then it would be greatly to your advantage to choose a coordinate system which lined up with the directions of those 4 forces. Then when you resolve your forces in step 4, you'll have an easy job of it with 4 out of the 6 forces. And number 4, as I said, is now you resolve the forces in your coordinate system. And when you first start doing these problems, it probably will be useful to you to make a little table and write the x and the y components of each force in your little table. And then when you come to step 5, where you apply Newton's first law, you can just plug things in. So step 5 then essentially says, take all the x components of all the forces in the problem, set them equal to, sum them up and set them equal to 0, then do the same thing for the y components of all the forces. And finally, you come to step 6. Step 6 says, do you have as many equations as you have unknowns? If the answer is yes, then you solve them and you're done. If the answer is no, which it won't be in the examples I do on this video, you have to go back to number 1, choose another body, and start all over again through the rules of the game. Okay, so everybody got the rules of the game. Let's go on to the first problem I want to do. Suppose I have a coffee cup sitting on a table. Suppose the coffee cup has a weight of 1 pound. I want to know everything I don't know. And essentially everything I don't know is the force that the table exerts on the coffee cup. Okay, so choose a body. Okay, I remind you, we're going to do number one now. We're going to choose a body. Well, guess what? I'm going to choose the coffee cup. Okay. Draw a diagram. Well, I've already started. I've drawn a picture of the coffee cup sitting on the tabletop. Now what I want to do is I want to say, what are all the forces on the coffee cup? Well, there's one that we always know is present, and that's the weight of the coffee cup. So let's draw that guy in here. And maybe I should just label it W. In fact, let me just freehand it here, okay? Okay, I'm going to get better at this as I go along, I'm sure. Okay, now, are there any other forces on this body? Is there anything else in the universe which might be exerting a force on this body? And the answer is yes, the tabletop must be exerting a force on this body, because if it didn't, the body would not be in equilibrium because there would be an unbalanced force. Okay? Do we know that force? The answer is no. That's what we're trying to use Newton's first law to do. And so I am going to say that there is some unknown force. Whoops. Got to get the pen here. There we go. Some unknown force, which I will call F. Okay? And are there any other forces on the body? And the answer is no, that's it. At least in our order of approximation. One could say the moon exerts a force on it, or the black hole at the center of our galaxy exerts a force on it, but these forces are so tiny that we are going to ignore them. Okay, next thing is choose a coordinate system. Well, the one force that I know is W, and incidentally, let me just simply say that W is equal to 1 pound, okay? So W is 1 pound in magnitude, and it's vertically downward. Since this is a force that I know, I might as well align one of my coordinate systems with this force. So I'm going to draw a coordinate system which has a positive y-axis in this direction and a positive x direction like this. All right, resolve all your forces. Well, let's do as I suggested before. Let's make a little table. Okay, so we've got W sub x equals, okay, the x component of W is equal to 0. The y component of W, notice that it's pointing in the negative y direction, and so that's equal to -1. Okay, f sub x, I'll just call f sub x, and f sub y, I'll just call f sub y. Okay, and if you want to draw those two guys on here, they look like this. Whoops. Let's see if I can use the eraser. Okay. Let's go back to this. F sub y and f sub x. Okay, now let's go back and see where we are. We've just resolved all the forces, and so now we apply Newton's first law. So we go back to this guy and we say the sum of the forces in the x direction has to be equal to 0. And that's equal to -1 plus f sub x. And that tells me that f sub x equals 0. And the sum of the forces in the y direction equals 0 is equal to -1 plus F sub y, and that tells me that F sub y is equal to 1. Okay. In other words, guess what? I certainly hope that you saw this coming. I've gone through and solved the problem formally, but the simple fact is that you could have done it in your head. Since there's only one other force, it has to be in the opposite direction as the one you know and have the same magnitude. And that's what we found by solving this problem out. Okay, let's do another problem. Same problem, except now I'm going to tilt the tabletop up a little bit. Okay, so now I have my 1 pound. Okay, so here's the weight, which is 1 pound. Okay, so I have my 1 pound coffee cup sitting here like this. And now I ask you, is there anything else in the universe which could be exerting a force on this guy? And the answer is yes, the tabletop. Okay, and this guy is not sliding down the table. I hope you understand that. Okay, so it's just sitting there in equilibrium. This is a Newton's first law problem. It's not sliding down the table. It's just sitting there, and you all know that you could lift up your table and your coffee cup wouldn't slide when it first started to tilt. Are there any other forces? The answer, of course, is yes, the tabletop. Now, I think I shall not do this problem in the gory detail that I did the horizontal tabletop, because now let's all acknowledge that we know what the answer is. What is the force that the tabletop exerts on the coffee cup? It must be a 1 Newton force. Okay, so here is the force F. It must be a 1 Newton force which acts vertically upward. Okay, so the magnitude of the force F is 1. Okay, and the magnitude of the force W is 1. Okay, and they sum up to 0. And yet, I think that you would agree that there's something different about this problem than the other problem, even though conceptually it's just the same. If there's only 2 forces and one of them is straight down, the other has to be straight up. But this is a different kind of situation. Okay? That is to say, F really is doing 2 different things here. Okay? Let me try to clean that up a little bit. Okay, let's try that again. Okay, so here is let's call this. Let me choose a coordinate system here. Let me choose a coordinate system that is has x this way and y this way. Okay, so here's plus y, here's plus x. Okay. So here's fx and here's fy. Okay. Those 2 components of the force that the table exerts on the coffee cup are qualitatively different kinds of forces, because F sub x is a force which is keeping that coffee cup from sliding, and F sub y is the force that is keeping that coffee cup from breaking through the tabletop. F sub x is called the friction force. Whoops, I realize you guys are often not taught cursive writing, so some of you might not be able to read this. And F sub y is called the normal force. Okay? Often in problems, I will denote friction by a small f. That will be the frictional force. And I will denote normal by capital N. Those are sort of standard notation for frictional force and normal forces. So although when we start doing more complicated problems, we're going to talk about frictional force and normal forces, I want everybody to remember that what's going on here is that these are just the two components of the force of contact between the surfaces which are in contact. And we'll talk in a little bit in more detail, of course, about friction later on. Okay, now I want to go now to an analogous situation so I can talk about a different kind of contact force. So once again, I have a coffee cup. Now my coffee cup is hanging from the ceiling by a string, and it's sitting there in equilibrium. Okay? Choose a body. I choose the coffee cup. Draw a diagram. Well, most of it's drawn. I'll draw now the forces on it. There is the force of the weight of the coffee cup. So here's W. That's equal to 1 pound. Okay. Are there any other forces on the coffee cup? Of course, the answer is yes. And if you think about it, okay, it's now, but it's not the tabletop holding it up. Now it's the string holding it up, okay? So the string exerts a force on the coffee cup, because if the string weren't there, the coffee cup would fall to the ground, okay? And again, I could go and I could say I'm totally ignorant of what the force of the string on the coffee cup is, and go through the procedure that I did back in this problem, the horizontal tabletop, but I won't. I will say, okay, we're all smart enough to know that since this is such an easy problem, that there will be a force in this direction, which I will call T, which is the force which the string exerts on the coffee cup. And if we now say, what is T? Okay, then the magnitude of T must be 1 pound. And T is called the tension in the string. So it looks a whole lot like the original problem that we did, but there's something different about it. There's this tension in the string. Incidentally, here's something interesting. This is the tension in the string down here. This string, incidentally, is a string which has no weight. Okay? Of course, there is no such thing as a string that has no weight. Nevertheless, if this is a pound, then this little piece of string is likely to be way less than an ounce. And so we just ignore that, okay? But suppose that I would choose a different body. Suppose I choose as the body now the string plus the coffee cup, okay? Okay, so if I choose that as the body, then the weight is the same, but now what we have is let's see, let me erase this for the moment. Okay, so I'm going to erase this, and I'm going to erase this. Okay, and then go back to the pen. Okay, so are there any other forces on the body? Well, yes, there's the ceiling up here. The ceiling is attached to the string, and the ceiling must therefore be exerting a force on the string, which is keeping the string plus the weight from falling. Okay, and so now there is a force at the top, which I will call T prime, another tension. That's the tension at the top. This over here was the tension at the bottom. Okay, but you can all see that T prime must be equal to 1 pound also. Therefore, the tension in the string is the tension in the string is the tension in the string. the tension anywhere in the string, which is the force the string that the string exerts on something, is always the same if it's a weightless string. Okay, now let me remind you what we did back here. We had the guy on the horizontal table, and then we tilted the table. So I'm going to do the same thing now for this problem. I'm going to say, okay, let's tilt the string. And now I'm going to tell you that this thing is in equilibrium, and I'm going to ask you to solve for what the force that the string exerts on the weight is. Okay, so once again, we have our weight of 1 pound down like this. And once again, without going through all the steps of the rules of the game, we have a force, let's call it T again. Okay, that's the tension in the string. And that has to be vertically upward, and that has to be such that T is equal to 1 pound. Right? You all believe that? There's something wrong, isn't there? Okay. So there is something different about a string and a tabletop. Okay. Because you see, this situation is impossible. You all know that. Just imagine having a coffee cup hanging from the ceiling, pulling it back, and letting go of it and telling it to be in equilibrium. It won't be in equilibrium because a very simple reason. The string is capable only of exerting forces along its own length. So let's get rid of this long tension. Okay. And come back and say, okay, what's going to happen in the real world is the tension in the string is going to look like this. Okay. And there is no way that this vector and this vector can add up together to be 0, and there is therefore no way that this guy is going to be in equilibrium. And this, of course, is what we call a pendulum. You all will study a pendulum later in the year. Okay, so that sort of brings me to the end of my simple Newton's first law examples. And just to get you thinking about tensions and strings, normal forces, frictional forces, they're all contact forces that you'll be encountering again and again in these problems, but that you will have to have sort of a feeling for in order to do the problems. And again, the rules of the game, if you follow these, you're going to see that they're going to work out great. So in the next tutorial, I will do a bunch of, not a bunch, a couple of less simple examples of Newton's first law problems. And we're going to probably have to introduce Newton's third law in the next video as well. Okay, that's it.